Thank you very much, Anubhav. Thank you very much, Mani. So it's a pleasure to discuss today and to present some works that has been done by different groups. And
I think you're on mute, Theory.
No, sir, we can hear.
No, I can hear him.
Okay. So if it is okay, for Mani, maybe I know you can check what's going on. So today I will speak about nonlinear interfacial waves during the first part of the talk, and then I will consider nonlinearities fully for internal waves, and I will discuss stability of internal waves. The first part will be rather low level with a lot of movies. The second part will be more advanced. So it depends if you are advanced or not in this field. So you can start and wait for the second part. In 2 days, I will give another talk about hydrodynamic solitons. There are some connections that I will discuss more on Friday morning or Friday afternoon for people in India. So I will speak about stratified fluids. I know that you attended the lecture by Professor Mathur yesterday, and there will be other talks about stratified fluids. So a fluid which is stratified is a fluid where the density rho is a function of a spatial variable z, which could be the altitude or the depth. So you have two examples on the picture. You have the atmosphere and the ocean, in which the temperature and the salinity are a function of the vertical, of the altitude or of the depth. Today, I will speak only about stably stratified fluids in which d rho dz is negative. So we will not have a convective phenomenon that we are used to, but we will discover very interesting phenomena that are called internal waves. I will start with a very simple experiment with a very specific question that has been raised by a Norwegian explorer. His name was Fridtjof Nansen, and he has a very interesting boat, very new at the time. And in some cases, he discovered that his boat was not able to move very fast. So if you read what is written on the slide, you see that when caught in dead water, the boat appeared to be held back by some mysterious force. In calm weather, the boat was capable of 6 to 7 knots. When in dead water, it was unable to make 1.5 knots. So I will explain what are dead water. You will see in experiment in a minute. But for Nansen was in Norway, in which you have a lot of snow, which is which can be melted because of the sun, and will be falling on the top of the sea. So you have the surface of the sea, which is with very few, which is not salted at all, and the bottom is salted water. So I will reproduce such a problem by a very simple experiment. Such a problem was the PhD thesis of a name that some of you may know, Ekman. It's a very old PhD thesis in 1904, in which you have dense and salted water, and above you have light and fresh water. Leo Maas, I will come back several times about Leo Maas, who is a Dutch physicist, a very good Dutch physicist that I'm collaborating with. So the idea is to put a boat on such a system and to play with you will have a rope, and the rope is pulled with a constant force, and the point will be to follow the behavior of the boat. And as a physicist, we can play with many different parameters: the tension of the rope, the weight of the boat, the depth of the different layers, the freshwater top layer or the salted bottom layer. The difference of densities also is an interesting quantity. So there are many different parameters, but today I will present only one experiment to show what are internal waves. So I played with the boat that is on the slide. Actually, initially it was the boat of my son, and you see, to play with the weight of the boat, we can have the fish or without fish. So the experiment will be shown here. We have a camera. So you have the boat. We have, in that case, salted water, and the top layer is with fresh fluid, and the bottom is salted water. And there is a rope that is very thin that you can hardly see on the movie, that will pull the boat as constant force. So it's very important to understand that, as you will see in a minute, the velocity of the boat is not constant, but the pulling is constant. So the idea is to pull the boat and to look what's going on below the surface of the sea, in some sense. So the boat is starting, and you will see that there are some perturbation that is visible up. So the boat is starting, and you will see some perturbation at the interface between the fresh water and the salted water. You see that the amplitude of the wave is quite large, typically of the order of the depth of the layer. And you see also that the wave is very fast. And as you will see in a second, it will catch, in some cases, the boat being destroyed, and the boat is starting again. And there is some oscillation in this behavior. But it's very important is that if you are on the boat, you see the boat is almost stopped in that case. So if you are on the boat, you see the boat speed, which is moving, but you hardly see any perturbation on the surface. It's flat. But below, there is some large amplitude waves at the interface between the salted water and the fresh water. These are typically interfacial internal waves that I will discuss in the first part of the talk. So what you have to remember is that the free surface is unperturbed, but below there are some large amplitude interfacial waves, and as the velocity of the waves below are an increasing function of the amplitude, they will catch the boat and they will stop the boat. So there is some complex oscillatory dynamics between the boat and the waves that is interesting. So this is another case where, in that case, you have three layers: pure water on the top, very salty water, salted water in yellow at the bottom, and some intermediate density in between. We can do the very same mechanism. We pull the boat at constant force. We will see that the boat is starting. There is some perturbation at the interface between the different layers. The amplitude is pretty large, typically of the order of the size of the different depths of the different layers. Because the amplitude is increasing, the velocity of the waves is increasing, and at this point, the boat is catched. Then the wave below is released and the boat can move again. So this complex oscillatory interaction between waves that are generated by the boat and waves that can catch the boat is called the dead water phenomenon. Because in the different examples that the Norwegian explorer discovered 150 years ago, he was in the boat. He was unable to understand why his boat was not able to move faster, and he was not able to understand what's going on. And actually, the dead was almost dead, completely flat, and this is the first reason to call this the dead water phenomenon. The second reason is that, as we know, when men are not able to understand something, usually they take guns. And actually, in that case, people on the boat were using guns to kill the body, the god, I don't know, the devil that was below the boat and was trying to catch the boat. Of course, there were no devils, there were no gods. There was only this complex fluid mechanics, but quite interesting problem. So let's look what's going on if we make a zoom. you can see for those of you who are more advanced in fluid mechanics that there is an interaction. We clearly see the different layers of the fluid, and we'll see some interesting billows, some instabilities. Actually, this is something like the Kelvin-Helmholtz instabilities between the different layers that makes the system not as simple as we can say initially. So to understand the physics, and actually because you followed the lecture by Mani yesterday morning, I think you can easily understand what's going on. But I'm used to present this slide where we make the analogy between surface gravity waves and some very simple mechanical analogy. So when you have a fluid which is at a constant density rho, and you have another fluid, the air above, it is quite usual to define the amplitude eta and to see the perturbation with respect to the depth of the fluid H. The mechanical analogy is to consider the oscillation of the position of a mass m coupled with a coupling constant k naught, and we can make some simple connections between some analogy between the oscillation of the surface of the fluid and the oscillation of the mass. In that case, the frequency depends only on the restoring force. In a case where you have two different layers, a fluid which is the air above, then a fluid of density rho naught, and below a fluid of density eta 0 and here eta 1, you see that in that case, the density is a step function as a function of depth. We have rho naught and then rho 1. In such a case, the mechanical analogy is a system of two coupled mass, m naught and m1, coupled by different coupling constant k naught and k1 and k2. And in such a case, depending on the difference of densities between eta naught, eta 1, and the density of air, then you can understand that it corresponds to the difference of coupling constant k naught, k1, and k2. And in such a case, you could have very large oscillations between the fluid at rho naught and the fluid at eta 0 and at eta 1, while on the surface, the perturbation is very small. If you put numbers, so I know that today we speak mostly about theoretical understanding, very simple experiment that we are able to do in the lab, but tomorrow Mani Mathur will present oceanic applications, and this is our goal also here in Lyon. So in the ocean, the perturbation, the difference in densities between the two different layers is very small. It's very small, typically of the order 1 over 1,000. And if you may put numbers, you see that if you have similar velocities in both layers, it means that the perturbation eta 1 could be 1,000 times larger than the perturbation eta 0. So typically, if you imagine that you have 10 centimeters for the surface perturbation at the surface of this fluid, eta 0, it means that you may have very large internal displacement, typically 100 meters, at the interface between the two layers. So it seems to be very huge, but it is really very important to understand that this is leading to very large amplitude internal waves, and the possibility to have internal displacement of the order of 100 meters is clearly a reality that I will discuss in a minute. Just let me come back to one single point. We have seen that in the experiment, the perturbation at the interface were typically of 2 centimeters, as you may imagine from the video. You see that it means that you can see some perturbation on the surface that will be of the order of a few millimeters or micrometers. So it means that if you are close enough to the tank, you are able to see some ripples. And indeed, on the video that I just showed, it was impossible and the surface was completely flat. But if you are very careful, you are able to see this very small perturbation. But at least, yes?
So rather than solving the equations, is there a physical way to understand why the displacement should be so large? The ratio of the displacement should be so large?
Yes, this is a point that I would like to discuss, of course. You imagine that the density difference between the air and the fluid at the surface is huge. There is a factor 1,000 between the density. So it means that as soon as the water is going into the air, there is a force which is huge that is trying to push back the water. While the difference in densities between the almost pure water and the slightly salted water, the difference in density is very small. So it means that when the salted water is trying to go towards the pure water region, the force is much less, and so the amplitude can be much larger. So this is the physical reason that is quite easy to understand. But as you will see, this phenomenon is huge. Could go up to 100 meters, but will be very slow. And this is one important aspect.
I see. Okay.
Thank you for your question.
Thank you.
Of course, anybody wants to ask a question, just come into just ask me. I do not see the chat, so it's there is absolutely no problem to ask questions. So this is a typical experiment that it's possible to do. I was just almost saying that you can do. This is an experiment that you can do in your lab or in your kitchen with your friends or with your family. This is not as simple as it seems, but it is not very difficult. You have to be very careful. You need water, you need a tank, and you need some salt and a boat. So this is the first case in which you have the spatial variable along the tank, and you have the time, and the color is showing what is the behavior of the perturbation that is visible when the time is running. So you see some depression, or on the contrary, so you see it's going below the flat, and it's above, and so there is some oscillation. And this is on the contrary, on the right. You have the velocity as a function of time, the velocity of the boat. So in such a case, you see that after some transitory motion, you reach a steady state where the boat is going at the same at a constant velocity. You pull at a constant force, and the boat is going at a constant velocity. But there is some other cases, and this is what we call the oscillatory regime, in which you have on the left, similarly, the evolution of the perturbation of the surface in color as a function of time. And on the right, you have the velocity as a function of time, where you see that the velocity is not reaching a steady state, but there is some oscillatory motion that is called the dead water phenomenon. So you have in this paper that we published some years ago, some more advanced discussion about this. So I would like you to understand the main ingredients for the analytical description of what's going on. So I will be using here in that case some work that has been derived by Vincent Duchesne during his PhD thesis. You have the paper at the bottom of the slide, where he was able to derive asymptotic models for the generation of internal waves when by a moving ship. So the article is not very easy to read. It's typically for mathematicians, but quite interesting if you are able to read it carefully. So what you have to understand is that if this experiment looks very simple, it is a difficult problem. It is a difficult problem from the mathematical point of view. Not only because you have partial differential equations, this is usual in field mechanics. You have also some strong nonlinearity, and it's very important to keep the strong nonlinearity and not to reduce to the linear approximation. And there are also some non-local aspects. So the idea that is usual in such a case is to develop an asymptotic model with some hypothesis and to show if you can apply this, use this hypothesis to simplify the problem and derive an equation that you are able to describe. So we have our system with a boat above a two-layer fluids with some, and we are interested in looking for perturbation at the interface between the two layers. So the first hypothesis that is quite easy to understand is to consider that the surface is unperturbed. And you have seen that we are physicists after all. We have seen that the perturbation is very small. I told you that if you are going close enough to the tank, you will see some ripples, but they are difficult to detect because very small in amplitude. So it's a very good approximation. We will forget everything on the top. It is a flat ceiling. The second point is to consider the approximation that you have a boat which is only a small deformation with respect to the depth of the fluid. So instead of having a deep boat, we will consider a very thin boat. This is an approximation that simplifies greatly the mathematics and the derivation, but it is that can be discussed. And if you compare to the experiment, you can agree that it is. We can argue about this problem, this hypothesis. The third one is to consider that the deformation of the interface is small with respect to the depth of the fluid. This is a small perturbation. This is again a perturbation that is not completely accurate, because we have seen that in our case we have typically perturbation of the amplitude of 2 or 3 centimeters for layers which are 4 to 5 centimeters. So 2.5 is not so small with respect to 4 or 5. But this is very important to be able to derive the equation that I will get in a minute too. And finally, the idea is to consider that oceans, or even our experiments, correspond to the shallow water regime. It seems to be strange, but it is a very accurate approximation, contrary to the number 2 and number 3. And you can understand many problems by considering the shallow water regime for oceans. So let me introduce 2 variables, which is the position of the boat, that I will call eta, and the position of the perturbation, that I will call psi. So using the different hypotheses, Vincent Duchesne was able to get this partial differential equation that I will try to introduce. So d over t means the time derivative of psi, which is the position of the wave. Then you have d over x, which is the spatial derivative again of the wave. And then you have a nonlinear term where you have 2 different parameters, epsilon and lambda. And you have the shape of the wave, time is spatial derivative. Then you have a third derivative, spatial derivative of the perturbation of the wave. And on the right-hand side, you have eta, it's the position of the boat that is moving at a constant, at a velocity c. And you have here d over x, which is the spatial derivative of this motion. So I skip the details between the fluid mechanics equations, the Navier-Stokes equation applied to this problem using the hypothesis. I just go towards this equation because I would like this first part to be at a rather low level. If you want to know more about the derivation, go back to the Vincent Duchesne's paper. You have all details. But I would like you to understand the different physical ingredients that are hidden in this equation that is very important. But what you see is that you have on the left-hand side, you have the evolution of the shape of the wave, c, and on the right-hand side, you have the motion of the boat. Typically, the position of the boat is eta, and so it's a forcing So clearly, you are forcing through eta the perturbation of the interface between the two layers. So there are different terms in this equation that I would like you to understand physically what's going on. So I call them transport, nonlinearity, dispersion, and forcing. This is what I would like to discuss here. So let me analyze this equation one term by one term. So I will keep on the left-hand side always the time derivative of the perturbation of the interface, which means the time evolution of the wave. And I will keep one by one the different terms. So let me keep the first term, d over x of psi, that I will call the transport. You can see on this movie, this is a solution of this initial equation, initial condition through this equation. So you can see on this movie that this term is not very interesting. It corresponds only to the translation of this initial condition, and it's quite usual. If you introduce, if you are like mathematics, if you introduce a spatial variable z, which is z equal to x minus t, you can change this two terms by only one term, d over z of psi, which means that you keep the initial condition constant in the moving frame, which is moving at the velocity 1 in that case. 1, because there is no term in front of the transport term, d over x of psi. Let's continue and consider now, we will keep only the nonlinear term, that is the quadratic term, which is typical for fluid mechanics, which is coming from the Navier-Stokes equation. And when we start with the same initial condition and look what's going on. And we see in that case that the system is on the right-hand side sharper and sharper, and you see a perturbation that is not moving, which is keep going towards what we call a shock. This term means that it's the region of the nonlinearity. Let's continue. And we keep now the third term in this equation, which is called the dispersive term. So in that case, we can see that the evolution is quite disturbing the shape of the initial conditions. We have perturbation of very thin wavelengths which are going very fast, and the coherence of the pulse is destroyed because of what we call dispersive effects. So in such a case, we have different wavelengths that can move at different velocity, phase velocities, and that will destroy the wave packet that you had initially. Now we would like to see what is the effect of the forcing term on the right-hand side. And this is typically what we get if you put c equal to 0. So in such a case, you generate a perturbation that is generated in the center and that will move slowly, as you can see in that case. So you have a perturbation that stays fixed, and one part which is moving towards the right. But things are different if you change c equals to 0 to c equal 1. This is the evolution. In such a case, c equal 1, in that case, you see that the perturbation is increasing in amplitude clearly and is diverging. Why? Because you remember that, so I will try to come back to the equation. You remember that I discussed that the velocity of the transport term here was 1. So if you force the system with a forcing which has a velocity equal to 1, then you have a very different response of the system with respect to the case where the velocity c is equal to 0. So this is typically the case. If c is equal 1, you have the divergence of the wave because there is a direct transfer, a resonance effect between the forcing and the equation of which is controlling the evolution of the interface between the two different layers. So now let's come back to the full equation where we have the transport term, the nonlinear term, the dispersive term, and the forcing term. And this is a typical result that you can get where you have in green eta, which is the boat. In blue, you have the interface between the two layers, and we will see what is the behavior of this system. So in such a case, you see that when the boat is moving, it is generating a wave at the interface between the two layers, and it generates a perturbation which is decreasing in amplitude and which is moving with the boat. But there is a big difference with respect to the experiment, that in that case, I'll solve the problem analytically, or actually Vincent Duchesne, I should say the truth. Vincent Duchesne solved the problem using the velocity c constant, while in the experiment, c was free. It was only the boat was pulled at a constant force. So in such a case, you are able to solve the problem numerically or analytically, partially analytically. And but this is not direct comparison, direct explanation of the experiment. It is closer to this experiment that has been done by Imre Jánosi from Budapest in Hungary. In such a case, his son has a boat which was different. You see, he has fresh water, salted water, and he was pulling the boat at constant force. So this is typically what Vincent Duchesne was solving analytically. So in such a case, the boat is moving at constant velocity, and you see that behind the boat, there are some waves which are clearly present and that are following the boat for many cases. And you see the damping effect, but it is very clear that is very similar to what Vincent Duchesne was able to derive. So depending on the cases, you may have an increase of the velocity, and then you can get towards stabilization, a steady state of the velocity, or you may have an oscillatory motion. It's something that you are able to do in experiments, that you are able to understand partially mathematically, but there is no clear explanation of what's going on really mathematically in the case where you pull at constant force. So let's go beyond and discuss what could be the applications or the consequences of such a simple experiment for our world. So if we consider the ocean, we have indeed, and I guess Mani will discuss that point deeply tomorrow morning, we have a fluid which is stratified. In the ocean, the density rho is a function of the depth, clearly, where you have water at the top which is salted but not much salted, much less than below or close to the bottom. The typical depth of the fluid could be 1 kilometer. The mean value is around 4 kilometers around the world. But you have a threshold which is called a thermocline, whose depth could be between a few hundred meters to 1,000 meters. It depends, where you have a jump in the density. So something which is similar to the experiment that I was discussing. And the evolution of this perturbation can hardly be seen from the surface, where you may have some perturbation. And actually, as you will see, in some cases, there could be a consequence of the perturbation below the surface. But the behavior of this fluid interface could have very large amplitudes, could have waves which are moving at rather slow velocity. You see 2.5 meters per second, sometimes less. But the amplitude could be quite large, typically 100 meters. And actually, if you are able to look on the right-hand side, this is a typical image that you can get from satellite, where you see some ripples on the surface of the ocean that are nothing but consequences of the perturbation below. I told you that in the experiment, we had a perturbation of typically 2 to 3 centimeters between the two layers and a few micrometers for the surface of the fluid. If you put numbers, you can get, as we discussed briefly earlier, we can have perturbation of a few centimeters on the surface of the ocean, which are traces or signatures of perturbation of typically 100 meters below the surface. And you have on this picture the different soliton trains, or these different waves that are moving in this. In that case, it is the Andaman Sea close to Thailand. So I would like to discuss that point with some picture. This is a case where this is a Messina Strait between Italy and Sicily. Sicily is a part of Italy in Europe. And an image showed that is presented on this slide shows some very huge perturbation. And you see that from the side that there cannot be waves or typical waves that you are used to. We can make a zoom, and you see that on the zoom, you have some boats that are visible. And you clearly see that the waves are much larger than the boat. So the internal waves that are generated in the Messina Strait are not generated by the boat, but are generated by another mechanism that can be described, and that I guess Mani will discuss tomorrow. This is another picture that I like quite nice, that I like very much, and I think it's quite nice. This is a case where you have the Philippines, you have Taiwan, you have the Luzon Strait, and you have China. This is a South China Sea, which is a part of the world which is very well studied for many different reasons, especially geopolitical reasons, but also there are some interesting aspects from the oceanographic point of view. And waves, internal waves, are generated by the interaction between tides and the bottom topography. You can maybe see a few islands north to Philippines, and actually between Taiwan and Philippines there is a very important bathymetry with a lot of seamounts that can be quite high, and because of the interaction between the tides and the bottom topography, there is a generation of internal waves that are generated and that are propagating towards the west and are generating this very elongated perturbation that are traces or signatures of perturbation of what we call soliton trades, underwater tsunamis that are propagating towards the left and that are typically generated by tides, so twice a day, and the amplitude is typically 200 meters every day. So it's very important, as you can imagine, from the oceanographic point of view. They will take fluids from the bottom and go and put this fluid at much less depth. And this is very important from the biological point of view. You can see on that this is a Doncha Island, which is there is a coral reef, which is very important from the biological point of view, and that is provided by planktons through these waves. And this is a phenomenon that is very well studied. Okay, so I'm almost finished with the first part of the talk. I would like to show you a few additional slides to show that, not slides, but movies, to show that internal waves are present inside the ocean, but could be present elsewhere when you have stratification. So this movie, the quality is not very, very good, but the effect is very important. So I would like to show it to you. So this is a webcam that is recording what the weather or the landscape outside from a TV house, and you will see the clouds that will be oscillating into the sky. So I will send the movie. And you have on the left-hand side, you have the clock. It's quite important for the physical point of view. So you see maybe the clouds, which are clearly oscillating in amplitude, and there are traces of internal waves that are propagating above this landscape. And you see that the clock is very slow. So to see this, you have a very large amplitude, but very slow process. So it means that from the analytical point of view, you may understand what's going on. So remember this, it will be important for many aspects. Very large amplitude, but slow process. Inside the stars, you may encounter also internal waves. Typical interior of stars are quite complicated, and the physics is very difficult to describe. But the density is clearly a function of the depth of the radius. And this is, for example, a movie that has been performed by Tamara Rogers. She was at Arizona University. Now she is in UK. So the density is a function of the radius. And in such a movie, you see what she was able to show numerically. You see perturbations that are propagating in this in the interior, which is stably stratified, and around close to the surface. In that case, the density is not anymore stably stratified. So there are some convective plumes that are excited by internal waves inside the interior of the star. So this is a physics which is quite interesting, difficult, but you clearly see that you have waves that are moving inside the earth of the star, and that are exciting plumes that may show some convective phenomenon around the exterior of the star. Okay, so I would like to conclude this first part by two papers to reference. Our papers that I was discussing by Mathieu Mercier and Romain Vasseur, who were the two students, very good students doing this experiment. And you have a very recent paper led by Germain Rousseau in the proceeding of the National Academy of Science, in which they are discussing what they call the dual nature of the dead water phenomenon. It could be interesting for you to have a look to this second paper. Okay. I propose to make a stop. I may answer to a few questions, and then we make a 5 minutes stop, and then I will come back to the second part. Do you have questions?
Sir, there is one in the chat box.
So let me try to find the chat box. Sir, is the energy pumped into the wave distributed? Oh, this is a difficult question, Raja. Yes, so it depends also very much whether you discuss internal waves inside the lab experiments or inside the ocean. Yes, when you excite waves, you excite different wavelengths. What is important to remember, if I want to stay at a basic level, is that in the lab, the dissipation is very important and will damp, especially small wavelengths, very fast. While in the ocean, the damping is much less important, and actually internal waves, or at least large modes, vertical modes. I think Mani presented this yesterday. So M1, M2, M3 are able to move over very long distances. We are used to say that they are able to cross the different oceans without being damped. So viscosity for the oceanic internal waves are not so important, and you can neglect viscosity. It seems to be quite strange, but it is quite accurate. This is a big difference if you want to make the comparison with experiments in the lab.
Excuse me.
Yes, go on.
So I don't see any term related to the rotation in the equation of that.
Because I didn't, yes, it's an excellent question. I should have discussed that point. Yes, rotation of the Earth is an important effect that I was not taking, putting into the problem to simplify. Of course, the rotation will take place, but typically, the typical wavelengths for these internal waves are a few hundred meters. And at the first approximation, it's possible to forget the rotation. But there's a big but. The physics of inertial waves, which are excited when you consider homogeneous fluid with rotation, is very similar to the physics of internal waves when you consider a non-rotating fluid which is stratified. And of course, there is, so the physics is very similar. There are some differences, but there are a lot of similarities that we may discuss more deeply later. And of course, when you have stratification and rotation, you have mixed phenomena that are very important. But for the first part of this talk, I wanted to stay focused on basic level, and I forgot this effect. You can't forget it if you consider the generation, the start of the propagation. But of course, if you want to consider and you want to understand the dynamics of the ocean, you cannot forget it. It's very important. So it's an excellent question. Thank you very much. Yes, Raja, they travel several thousand kilometers. That's incredible, but that's yes, the answer is yes. Okay, so I stop 5 minutes. I will have a coffee and I come back in 5 minutes. Thank you very much. Okay, I'm back. I propose to start by the second part. So as I was saying, the second part is more advanced for people who are aware of internal waves, more at least than what I showed earlier. And today I will speak about hydrodynamic solitons in a different way. I will use a blackboard, and I will try to do in the old style. And it will allow me to be more quite pedagogical. I expect you to understand what are hydrodynamic solitons and interfacial waves, as I was discussing a minute ago, is a good example of such a phenomenon, but not the only one. So if you are ready, we will speak about internal waves and discuss. I will discuss today by some introduction. Some of the work that I will show have been briefly discussed by Mani yesterday. I will be present in another way. And then I will discuss the triadic resonance stability, which is an important instability in which nonlinearity plays a very crucial role. And if I have time, I will discuss the streaming instability in the last part of the talk. But the objective is not to go too fast and to be more pedagogical than going to present too many things. So of course, you can continue to ask many questions. There is absolutely no problem. You stop me, and I prefer to go slowly that you understand that to present everything. So this is a typical image that has been provided to me by my colleague from Russia, from Novosibirsk, Evgeny Armanyuk. Mani showed yesterday a similar experiment in which you have a cylinder which is oscillating up and down in a stratified fluid. So you see a side view. You see the gravity is pointing downward. And this is the usual pedagogical introduction to internal waves, which is called the St. Andrews cross, in which the oscillation of an object, here a cylinder, is generating 4 arms with different colors, which are actually the faces of the different arms, and which are emitted from the cylinder away in 4 different directions. So we have lower density fluid at the top, larger density fluid at the bottom, and in that case, in most of the talk, I will consider a linear stratification. In that case, we are oscillating the frequency at we are oscillating the cylinder at the frequency omega, and it has been discussed by Mani. We have a very strange dispersion relation. Omega is equal to plus or minus n sine of theta, where theta is the angle between the beam and the horizontal. And n is called the Brunt-Väisälä frequency, where you have the definition on the slide. N is equal to the square root of minus the gravity divided by the mean density and the spatial vertical derivative of the density. What is very interesting, and now I'm doing experiments, or my students, I'm trying to find very good students to do experiments. But initially I was theoretician, and clearly it was very appealing for myself to see these waves in which you have an anisotropic propagation, and you will see many different phenomena that are quite interesting and that I would like to discuss. And anisotropy is clearly, of the propagation, is clearly a consequence of the anisotropy of the density. And what is important also is that it has been discussed, I guess, by Mani deeply yesterday, and you got almost all details. The dispersion relation features the angle of propagation, theta, but the wavelengths do not appear in the expression omega is equal to plus or minus n of sine of theta. And so this will have some consequences, disturbing ones, that I would like to discuss later in the talk. last point, the group velocity in which the fluid, in which the energy is propagating is clearly along the different arms. So it's pointing in for this right below, bottom right arm is pointing downward, is orthogonal to the phase velocity because the different colors, as I was explaining in this system, this is called the synthetic Schlieren technique that will be discussed by Silva this afternoon. In that case, the phase velocity is orthogonal to the group velocity. It is very strange the first time you met it, you met this result, but actually you can derive directly from the theoretical dispersion relation that is written in this on this slide. But you will see some consequences and you will get interesting surprises later in the talk. So these waves, these gravity waves play a primary role in geophysical fluids. Mani will discuss their application in the ocean tomorrow morning. There are also interesting application in the middle atmosphere. I will not go into this clearly into the details of this today. I would like to focus on mechanism, and I would like to be rather basic by saying that generation and propagation of these internal waves are now quite well understood. By contrast, dissipation mechanisms are still debated, and there are many different mechanisms that are able to explain this dissipation mechanism. The wave-wave interaction, the reflection on sloping boundaries, the scattering by mesoscale structures, for example, vortices, and the scattering by finite amplitude bathymetry. This is a still open domain of research to see what is the main important mechanism that will dissipate the energy put from the tides towards the internal waves. And there are very different groups around the world that are discussing this using numerical simulation, theoretical understanding, or experiments. Final point, this is one of our goals, is it's possible, and there were very interesting results initially in 75 by Garrett and Monk, two very famous oceanographers. It's possible to measure the energy spectra that internal wave will follow into the oceans, and how we can get from the single wave emitted in close to a seamount because of the interaction between internal tide and the seamount, the creation of this internal wave towards the interaction of wave-wave interaction towards this energy spectra is still an open question that different groups would like to understand. So let me go into some equations that I would like to discuss. Some of them were discussed by Mani yesterday, but here I would like to keep the nonlinear terms. Physics is very interesting when you keep nonlinearity, slightly more difficult, but very interesting. And you will see that especially for internal waves. So the typical equations that are used is we take fluid velocity that I will call U. I will consider an incompressible flow. So the divergence of U is equal to 0. Then we are used to take the Navier-Stokes equation with this left-hand side, which is quite natural. Then we have the pressure term with the density reference ρref. Then we have the dissipation term that will not be very important to the ocean, but that will be very important in the lab. And in between, we have the force due to Archimedes that I call B for buoyancy, which is pointing vertically. And you have written on the left the definition of this buoyancy field, which is different between the static density initially ρ0 of Z and the dynamics of ρ. ρ is a function of X, Z, and T. And this buoyancy term is the origin of the physics here of the internal waves of the stratified fluid, and everything is into this new term. And there is a third equation, third effect to understand and to keep in mind is the mass conservation, that is written. This is the third equation. So today, to simplify, and again, as it has been asked later by Mukesh, I think, I will forget the rotation of the Earth. So I will forget the inertial waves. That will simplify my discussion. And I will consider that waves are propagating into the vertical plane. So I will restrict the velocity field with two components. The horizontal spatial variable will be x, and the vertical one will be z. And so it's possible to introduce a stream function where the two different components of the velocity field u can be written dz of psi and minus dx of psi, where psi is the stream function. So it's possible, using this expression of the velocity field, to introduce this velocity field into the three first equations, and we end up with some equation that looks quite difficult initially. So I will not do the details of the derivation, but it is not very difficult. But you can get that you get two different equations. One, which is the evolution of the so-called vorticity, which is the nabla square of psi. Actually, you derive spatially the Navier-Stokes equation, the two different components, and you can get these two equations, where you get, this is the result, you get the time derivative of the Laplacian of psi, plus the Jacobian of the Laplacian of psi. The Jacobian is recalled below, and minus the x of b, plus the damping term. And the third equation that is written up there can be rewritten directly using this different formulation with the string function psi as it is written here. And you can combine these two equations to get one final equation that looks very simple, very difficult, but that I will discuss one by one the different terms. So on the left-hand side, you have the linear terms. In green, you have the viscous term, and in red, excuse me, you have the nonlinear terms. So the linear approximation is what Mani discussed yesterday. You have, I keep only the left-hand side that was done there. And you see clearly that the equation is, as I will discuss, a wave equation, but different from the D'Alembert's equation. You have a spatial derivative that are appearing on the second term, but also through the Laplacian on the left-hand side. So the spatial derivative are entering at the order 2 for the two different terms. So let's look for plane wave solution for this in this equation by looking for solution psi in the aspect psi naught exponential I k r minus omega t, where k will be the wave vector, r will be x and z, the two different components. You have a small drawing on the top right, and we will have the wave vector k with the wave numbers L and M. But it's possible to plug this plane wave solution into this equation and get the dispersion relation that Mani derived yesterday, and you can get quite easily using this equation. So let's consider the linear approximation. Once we have this plane wave solution, let's forget the nonlinear term that I derived earlier, because we are in this slide in the linear approximation. We see that there is a direct relationship between the buoyancy and the string function psi through an expression P, which is the polarizability, and which is the linear relationship between the buoyancy and the string function. So let me show what's going on. In an experiment, if you are able to excite through a generator, I think Mani will discuss this in detail. in a tank where you have a stratification, so you have a fluid which is stratified in density vertically. If you are able to excite the boundary at a frequency omega, then you will see internal waves propagating at an angle theta. So this is what is shown on this experimental movie. So in black, you have the position of the generator, and you see clearly that once you start the oscillation with a sinusoidal shape, you are able to excite waves quite well collimated that are propagating up, with an angle omega, with an angle theta. So you see, and Mani will come back later on this possibility to excite waves using generator. You see clearly that if you are able to excite moving boundaries at a frequency omega, then you are able to see internal waves propagating at an angle theta if omega is kept fixed. So this is a simple verification of what the linear physics is telling to you. Now let's come back to the nonlinear world, which is our world. So we have again the psi, the string function, b, the buoyancy, and we switch on the red term, which were these two terms. So clearly, these two terms are difficult because you have the Jacobian. You remember this is the multiplication of the two different derivatives, which is mixing the string function and its Laplacian, which is a vorticity, and on the right-hand side, mixing the buoyancy with the string function. But we can look for plane wave solution of this equation. We know that there are exact solution of the blue part if we follow the dispersion relation. But in that case, we can go further and see that the Jacobian of the string function, if it is a plane wave solution, we know that the Jacobian will give you, for the Laplacian of psi, will give you minus k squared psi. And the Jacobian of psi will be 0. So the first term on the right-hand side will be 0 if you are considering plane wave solution. Similarly, we have seen that there is a linear relationship between the buoyancy and the string function. So it means that here, in that on the second term on the right, you have p psi, which means that the second term will be also 0. So you get this very interesting result that for plane wave solution are not only solution of the linear version or the linear approximation of the equation, but that are exact solution of the full nonlinear equation. So for people who are used to nonlinear physics, this is quite strange. Linear solution are usually not exact solution of the full nonlinear equation. So it's the first interesting aspect. But, and this is very important, there are solutions, there are exact solutions, but it doesn't mean that there are necessarily stable solutions. Second point, and this is quite interesting, a uniform beam, which means a uniform beam at an inclined, which will be propagating at an angle theta with respect to the horizontal or the vertical. A uniform beam will be also an exact nonlinear solution regardless of its transversal profile. So plane waves are solutions of the nonlinear equation. Vertical modes are also solutions. And we can find many different solutions that we like to study the stability. So so this is what I just say, but I will skip this. It's better. So let me jump to some physical phenomena that are quite interesting for such a system. And I would like to focus on the internal wave reflection for this internal waves, because we have seen that linear physics, but also nonlinear physics, is emphasizing that plane wave solutions are very important, are exact solutions. It's quite interesting to study their behavior, especially when they will be reflect on boundaries. And I will discuss first on horizontal wall and then on inclined wall. So let's consider a blue ray that will hit the bottom topography. And the blue ray will be an internal wave at a given frequency omega, which means that omega is equal to plus or minus sine of theta. So it will propagate with an angle theta with respect to the horizontal. And of course, after reflection, it will keep its same frequency omega. So it should keep its angle with respect to the horizontal or to the vertical. Things are quite interesting if you consider the reflection on an inclined wall. So because you have an incident beam that is reflecting on the inclined wall, inclined to an angle alpha, we see that after reflection, because of the fact that the blue incident ray has a frequency omega and the red reflected beam has an angle at a frequency omega, it means that the angle should be kept, and we do not have the Snell-Descartes reflection that has to be fulfilled. We have a very different phenomena, and we see that after reflection, the angle with respect to the horizontal or the vertical will be kept constant. And we see in addition that the width of the incident beam is larger before reflection than after. So this is a phenomenon that is quite interesting, where we get a energy density that has to increase after reflection. So this is a phenomenon that is directing to energy focalization. But up to now, I was drawing this picture by following the dispersion relation. So I was following the linear dispersion relation. So I was considering a linear transfer to small scales. So this is quite interesting. Energy focalization using only linear transfer. So let me just give you some very fast view of different aspects of the nonlinearity for such an equation. So the two following slides will be very, you may find them difficult if you have no experience, but I will come back to more simpler aspects in a while. But I think they are important to emphasize that the nonlinearity in for such waves are quite interesting. In a quite old paper now with my colleague Bill Young from San Diego University, UCSD, at Scripps, we were studying, and this was my first encounter with antenna waves, the reflection of a beam on such an inclined surface with a reflection width which will be smaller, and so an increased density after reflection. So there is a linear transfer between scales, and it was possible to show using match asymptotic expansion that it's possible to find a solution of the case where alpha and theta are equal, in which we expect to have a divergence of the reflection of the not a divergence, but so I should come back to that point. Actually, when I do not have the slide here, slide is missing. Actually, when the angle theta is equal to alpha, then the reflection of this beam is along the bottom topography, and the width is infinitely thin. So there is a divergence of the energy density, and this is something which is a problem from the analytical top view, which is in fact due to the fact that you have forgotten that you have removed the nonlinear terms here in that case. But what I want to discuss today is the fact that using match asymptotic expansions, we were able to show that keeping the nonlinear terms that are supposed to yield this singularity, it's possible to get an amplitude equation in which the nonlinear terms that are in red are going on the side of the linear terms which are written in blue, and which are forced on the right-hand side by a forcing due to the cylinder, moving cylinder, or a tide if you are interested in the oceanographic application. What we get is very interesting results that the nonlinear terms, which are quite complicated, actually 14 terms, are equal to 0. The nonlinear term cancel out, and this is what, for people who know this is a special case of the Jacobi identity. So nonlinearity seems to have, again, a very strange behavior when we consider the nonlinear reflection of internal waves. And actually, linear dispersive effects and viscous effects, if you are considering especially lab experiment, will dominate the nonlinear effects. So it is one important reason for emphasizing that the physics that has been raised by Mani yesterday during his lecture is already a very large amount of the information that you need to understand what's going on. Nonlinearity play a minor role in some cases for these internal waves. A second point that I would like to emphasize today, which is again a bit advanced, is a work obtained by Triantafylos Akylas, Kevin Lamb, and Alita Bey, one of his PhD students, is the fact that if you seek asymptotic solution for a slightly viscous nonlinear wave, so you have a beam which is propagating into a stratified fluid with an amplitude which is slowly modulated along the longitudinal variable psi and in time, then again you get the nonlinear term, which are written in red, that will be cancelling out, and you have the physics which is driven by the linear physics. So again, dispersive and viscous effects dominate the nonlinear modulation of internal wave beam into the ocean. So the nonlinearity gives some surprise if you consider their behavior in this stratified fluid.
Sir, can I ask you a question?
Go ahead, Raja.
So this is about this focalization of energy. So the incident beams which are coming from left side, getting that inclined topography and getting energy is getting focused. These rays are coming very thinner and thinner, or perhaps coming close together. But if I reverse this energy focus direction in the other way, like incidenting waves from the right direction onto this bottom wall, and do they get separated out, or do they again come together?
Can you say it again? There is a strange noise behind your voice, so can you say it again?
Yeah, I'm really sorry. So it's basically, you have shown this energy focalization by incident waves. Two incident waves comes and hits the topography from the left direction, and they will reflect and go towards the right direction. While they are going, they come together so that energy gets focused.
Yes.
But if these waves are reversed, I mean, from the right direction, they come hit the bottom topography. Do they separate out, or do they again come together because of this nonlinear effect?
So your question is excellent. If the wave is going to, as it is shown here on the slide, it will be focused. But if you go into the other direction, it is not focused. You're right. So it depends on the value between alpha and theta on this, and of course the time of propagation. So you may have linear focalization, but you may have energy defocalization depending on the case. Yes.
I see.
This is a good
Thank
question.
you so much. Thank you so much.
So, so it's possible into the lab to excite waves, as I was saying. You use the generator. Mani will discuss this tomorrow in details. He has also used a similar wave generator during his PhD, and it's possible to excite beam quite easily into the lab. And there are different advantages because you have a well-defined beam. You have only one beam. You may consider cases in which the wavelength is smaller than the width. The emission is localized in space, so you can test analytical prediction quite easily. So so attend tomorrow his talk, and you will know more about this wave generator, where you may understand how to deal with in the experiment. I see that Yogesh would like to ask a question, maybe.
Hello, Professor Theory. So my question is about when you consider the viscous scenario in your nonlinear approach, does the dispersion relation change significantly compared to the linear approach?
It depends, yes. You can derive the behavior of the frequency when you consider the dissipative terms. It's not very difficult. Usually in the books, it is not well discussed because dissipation is not important into the ocean. But if you, for example, in all PhD students of my PhD manuscripts of my PhD students, you can derive this. It is explained in a few slides, so it's not difficult. But not very important either.
Okay. So, like, do you generally consider small viscosity so that you can neglect, or is it always the case that the viscosity is small that you can neglect? Like, is it an assumption or is it a fact kind of thing?
No, in most of the description of what's going on in the ocean, the viscosity is initially neglected, and then we consider it as a small perturbation, and it works quite well. Into the lab, you cannot neglect the dissipation. And as we are using lab experiment to understand the physics of internal waves, it makes a big difference. But so in the experiments, you always have to deal with the dissipation.
Okay.
Because you understand what's important, the viscosity of the fluid is the same, but the size of the tank is typically 40 centimeters. In our lab, we have a 2 meters tank.
Okay.
I made some experiment in a rotating platform where also Mani used to study some time ago, where it's a rotating platform at the diameter is 13 meters. So even in such a system, the viscosity play a quite important role, because the Reynolds number, which is making the comparison between the nonlinear terms with respect to the dissipative terms, because it's too small with respect to what's going on into the ocean.
Okay. So so do you also find refraction because of viscosity, or is it only reflection that we find in these kind of experiments and all?
Say it again, please.
So do we find a refraction? So you said energy focalization. Is it because it's not just reflecting, but it's also refracting?
Yes, there is also refraction, diffraction. This question is an excellent question. The understanding is not complete. So I will not discuss this today. We already discussed, for example, with Mani, we had some plans to work on this. Other people have done interesting work. So this is important, but still pretty open. So I think it's too advanced to discuss this today.
Okay.
If you don't mind.
That will be all from my side. Thank you.
It was good to have many questions here because I will switch topic. So we have seen that internal waves, plane waves, or internal wave beams are solution of the nonlinear equations, complete nonlinear equation. It's possible to identify such solution, but it doesn't mean that it's a stable one. And the objective of what I will discuss now is to present recent progress on the destabilization of internal wave beams. And I will try to study the nonlinear effects. So this is described in a paper quite recent, Annual Review of Fluid Mechanics, with my colleague Sylvain Joubot, Philippe Aubier, and Antoine Venaille, in which we present our work, but also different the work of different groups around the world. So it's a review paper. In some sense, it should be. It has been written to be pedagogical. I hope you may find it useful. So the stability of internal waves can be studied quite easily into the lab experiment. And I would like to show a simple experiment, again, very similar to the one that I showed a few slides ago, in which we have a generator on the surface, which is creating a modification of the boundary effect with plates which are oscillating up and down at frequency omega. And thanks to the dispersion relation, they will excite waves at the frequency omega that will be able to propagate in an angle theta with respect to the horizontal. So this is a typical image where you see the evolution. So I will start again. So you see, I'm sorry, the mouse is. You see the evolution of the beam, which is generated, which is propagating into the fluid. And after some time, we see a perturbation of the shape. Clearly, the beam is not stable anymore and is disturbed. And actually, there is an instability. So initially, it is okay. But after some time, there is an instability that is taking place. And that will be disturbing the propagation of the beam. In that case, in which the amplitude is larger on the right than on the left. So if you are able to follow the spectrum content, so this slide is not difficult to understand, but if I take the time to introduce it. So you have the time evolution horizontally, and you have the frequency vertically, and the color is the spectrum content. It means what is the quantity of energy, the amount of energy that is appearing into the system at the frequency omega as a function of time. So when the amplitude of energy is large, you have red. When it is very quiet, it's blue. So to measure this, we use what we call a time frequency analysis, and you have the definition at the bottom of the slide, which is not very important. Initially, we excite the generator at the frequency omega. So we excite the fluid at the frequency omega, and we see clearly that in that case, it's 0.75, something like that, that this is the frequency that is propagating from t equals 0 to t equals 200. But we see after some time the appearance of two horizontal lines. They are not completely horizontal lines, but there are two lines that are excited around 0.22 and 0.53. And you see clearly that they are excited. They are not present initially, but they will be created after some time, and then they are evolving. So the value around 75 is the primary wave that you excite into the system. And we have seen there is a destabilization of the beam. And the destabilization of the beam is clearly visible in this time frequency analysis by the appearance of secondary waves at different frequencies, omega, that I will call omega plus and omega minus, while the horizontal one is omega naught. And actually, you see that if you take a vertical cut of the frequency content, you have this quantity which is written up there, which is telling you what is the spectrum content. So you have a lot of energy around omega naught, the primary wave, which that you force into the system. And there is two different peaks around omega plus and around omega minus, which are excited through an instability that I will call secondary waves. And what is very striking is that omega plus plus omega minus is equal to omega naught. You can check this in that case, but we have performed several experiments, and it's always the case.
Excuse me?
Yes?
Can you please go back one slide? Yeah, the definition of energy, this expression in the model is, yeah, one slide forward, please. Yeah, this one. Yeah, so can you please tell a bit about the definition of this energy, rho times H?
Yes, yes, you're right. H is an Anning window. So this analysis is using wavelets. So it's trying to distinguish the different frequencies, and so there is a MATLAB code that will tell you what is the amount of energy for different frequencies. So yes, H is not defined here, so it's a problem. So it's an Anning window that will try to extract, to disentangle the different frequencies. Okay. You can use this as a black box in some sense. Okay. And because frequency and time are correlated, to extract the information is not so easy. And this tool is an appropriate one. So sorry not to have introduced what was called H. Thank you, Mukesh.
Okay, sure.
So we have seen that there are some there is an instability that will generate secondary waves that are excited by the system, and that I would like to know more about it. So let's take a simple sample experiment. After some time, we have this typical pattern. We had a generator on the top that is generating internal waves that are propagating into the fluid. We had a beam which was well collimated initially, that is destabilized, and we see clearly the destabilization, but we would like to know more about the destabilization. So we have seen that there are three different frequencies: omega naught, omega plus, omega minus. So the idea is to use the so-called Hilbert transform. So Sylvain Joubeau will discuss about the Hilbert transform this afternoon. It is a tool that initially theoretical tool that you can implement in experiment that will extract, that will filter actually, that will filter, but which is more than just a filter, that will filter what is the spatial variation of the perturbation at frequency omega naught, omega plus, or omega minus. So if you filter this beam at frequency omega naught, you get the initial beam that you add that is stable forever, but actually the result that you get, which is destabilized, is due to the appearance of two different secondary waves, omega plus and omega minus, that have different inclination, that have different amplitudes, and which is going in amplitude. Initially, you have only omega naught, and because of the destabilization due to the instability, you have the amplitude of omega plus and omega minus beams that are increasing in time. Moreover, we know, because of the dispersion relation, that a frequency omega naught is associated to an angle of propagation theta, which means that different frequency omega naught, omega plus, and omega minus will be associated to different angle of propagation, theta naught, theta plus, and theta minus. And we see from these experimental measurements that clearly different frequencies imply different angle of propagation. And this is the reason of the appearance of the destabilization. And we see on the top pictures that there is a perturbation on the top left corner that is emitted on the left of the beam, because clearly this is due to the omega minus beam, which is more horizontal than the original beam.
I have a question.
Please.
Your omega plus and omega minus is itself varying in time, right? If you see the previous slide.
Good question. I see that you are good. No, so yes, you're right. Omega, so this is omega minus, is almost constant and then varying. Yes, in principle, yes. When we do the experiment, when I was doing the experiment, I was keeping omega plus and omega minus constant, while in the experiment it is not. So it's an excellent question that I do not take care of in this analysis.
Okay. But for this plot, which omega plus and omega minus have you chosen?
So I'm choosing this one. So you see for omega minus, it's almost constant during some time, and I'm doing the analysis around 50. So I am clearly in a situation where omega minus is omega almost constant, or omega plus is constant. But you're right that when we are going up, when we are going towards t equal to 100 T0, by the way, omega plus and omega minus are evolving. But again, I'm analyzing around 50. Okay.
Okay. They can also decay over time. That's what we are seeing, right, in the previous slide.
Yes. It's a complicated phenomenon. So you are quite smart. So, but I cannot discuss this today. But you are fully right.
Yeah. Thanks.
And to be completely honest, this is a point that is not completely clear for us, and we are trying to understand this. So if you have good ideas, write to me. We can discuss about this.
Sure.
This is an important effect. But you can see that omega plus and omega minus are evolving in time, but the sum is always omega naught.
Yes,
okay, you see that when omega is going down, omega plus is going up. So, but this is a point that we do not control completely experimentally. We have some ideas theoretically, but it's not completely clear.
Yeah.
But this is a very good question.
Yeah, thank you.
Yes, so using the Hilbert transform, so which is for that point, it's some kind of filtering. So the idea of using this Hilbert transform was given to me by Nicolas Garnier, who is a colleague of mine here in Lyon, and we implemented with Mathieu Mercier, former PhD student who was doing the experiment with the boat that I discussed earlier. So in this paper, so we can do more. We can compute the phase using the Hilbert transform. We can compute the phase of the different signals. So we had on the bottom of this slide the three different filtering at omega 0, omega plus, and omega minus. And we can compute the phase. The phase means that we have a beam which is propagating with a phase that is written, that could be written as Lx plus omega mz minus omega t, with different inclination, and from the experimental data, it's possible to compute the phase, and it's possible to derive the phase phi with respect to x, with respect to z, and again to respect to the time. But what is important is that you can compute d phi dx, which will give you L. You can derive d phi dz, that will give you m, and so you are able from experiments to derive the components of the wave vector. So this is what I've done on this picture. It's possible to compute the wave vector, which is colored in black for omega naught, the forcing frequency. The red one for omega plus, the first secondary wave, and the green one, which is for omega minus. We can compute this from experimental data using this value. And what we get is that the sum of the three different wave vector, the sum as it is written in yellow, is equal to 0, which means that you send into the system the wave vector which is in black, and you have a destabilization of this incident beam, which is giving rise to two different frequencies, omega plus and omega minus, and each of them is associated to a wave vector k plus and k minus. You have to remember what Mani taught us yesterday, that for a given frequency omega, there is not a direct link between omega naught and the wave vector k naught. It has to be, there is a freedom, which is quite new for people who are not used to internal wave. But clearly, lambda or k is not appearing into the dispersion relation. So in that case, we have some freedom. So we find that thanks to this freedom, the system is able to excite omega plus and omega minus frequencies with very specific wave vector k plus and k minus, so that k0 is equal to k plus and k minus. This is not clear. This is clear from experimental data, but it was not given a priori. So it's possible to do this theory of this triadic instability, and the first to have done this was done. So it was been done by Makewan and Plumb in some time ago. Most of you were not born, of course, but I was. But I was not reading articles at that time. So let's start with the equation that I derived earlier, the very same equation linking the string function and the buoyancy. And we will be looking, we will seek solution of these two coupled equations, two nonlinear coupled equation, nonlinear through the Jacobians. We will look for solution using the sum of plane waves that we have seen that they are each of them exact solution of the nonlinear equations. So we look for sum of plane waves with amplitude for the buoyancy, which will be written as R and Rgi for each plane waves, and the same thing for the string function psi. And it's possible to show that we can get from the theoretical derivation that provided the spatial and temporal resonance condition, so the spatial one is k0 is equal to k plus plus k minus, and the temporal condition omega 0 is equal to omega plus plus omega minus, then we get the amplitude equation, which will deal the time evolution of the amplitude of each plane wave. And you have its expression at the bottom of this slide. D over dt of psi plus or psi minus is written by some nonlinear terms, which is quadratic, psi naught, which is the amplitude of the initial beam, and plus psi minus or psi plus, which is amplitude of the other secondary wave. And in front, you have a prefactor, which is a geometrical prefactor, where the different wave components of the terms is entering into the expression. And on the right-hand side, you have nu, which is a viscous term, times the wave vector k plus or k minus to the power 2, times the amplitude psi plus or psi minus. So this is an equation that you can get, and then you can check. And you see that if psi naught is important, you may expect a linear growth, an exponential growth of psi naught, psi plus and psi minus, damped by the right-hand side term. And this is a picture which is quite difficult to understand. But there are different, as I was explaining, there are different, there is a freedom for the choice of the wave vectors, because a given frequency omega is associated to any value of the wave vector. There are different freedoms, there are different triads, but among them, there are some of them are more important than others. And for example, it's possible to compute the growth rate, sigma, as a function of the wave vector k plus or k minus. And you have different patterns. So whether you have a very large value of k plus, which means very small wavelengths, or a very small value of k plus, which means very large wavelengths, you have different shape, different growth rate. So you have a system where you have initially only omega naught and k naught, but because of these possible instabilities, you may wait and you may see appearing different wave vectors, different secondary waves. And you see that in the inviscid case, which is a oceanographic case, you see that you expect to have very large value of k, which means very small wavelengths that will be more that have more ability to grow. While if you are considering the viscous case, you will kill the growth of the large wave vector because the small wavelengths are very damped by the dissipation, and you may see much smaller k plus value emerge instead of with respect to the inviscid case. And this is the difference between the parametric subharmonic instability, what we call PSI, which is the case where you have the inviscid dynamics, that you expect to have very large k plus secondary waves, with respect to the triadic resonance instability, that is maybe a more general denomination that is very valid also for viscous fluid. But in all cases, it is an instability which is due to the quadratic term of the Navier-Stokes equation that will drive secondary waves that will grow in amplitude in a system like the stratified fluid that we are considering. So there is a good agreement between theory and experiments, but we have seen that the central curve is always a larger growth rate is more attained than case. So
can I ask a question?
Please.
Is there any relation to the inverse cascade found in turbulence to this phenomena?
Say it again.
Is there any relation of this phenomena to the inverse cascade in turbulence?
Not really. It is not completely disconnected, but this is not. So a cascade is a transfer between wavelengths, but this is not directly linked to the inverse cascade. No.
Okay. Thanks.
Okay, I have only 5 minutes, so I'm a bit too so my talk was too long, or I'm too slow. I don't know. Anyway, so I will skip this. I would like to conclude with an effect which is quite interesting, which is a finite width effect. If you have an unstable beam, as I'm discussing, let's imagine that you are considering this domain, which is a rectangular with the width omega and the length L, in which you expect to have an instability with an initial wave vector k naught and two unstable wave vector k plus and k minus that are inside this domain. We see clearly that because the wave vectors are orthogonal to the group velocity, because the phase velocity is along the wave vector, and we know that the phase velocity is orthogonal to the group velocity. So we have a beam in which we have a black evolution of the main beam with the frequency omega naught, which is giving rise to two unstable secondary waves, omega plus and omega minus, which are propagating in a different with a different angle of propagation, sigma plus and sigma minus, which are not aligned with the beam. So part of the unstable of the two frequencies which are unstable will be emitted away from the rectangular and not aligned with the rectangular. This is a phenomenon that is quite easy when you get it, but which was quite disturbing for us, you see, only 6 or 7 years ago. and actually which explain some of the experimental result. And actually, if in the system you are exciting an instability in which the energy is emitted on the side, it means that the transfer of energy or the extraction of energy from the main incident beam towards the unstable ones is less efficient, and it explains why we obtain some differences between theoretical prediction and experimental ones. So maybe you can have a look to the paper. I think it's time to end, and I'm a bit. I won't be able to conclude to present the last part of the talk, but I think it's better. I would like to conclude by thanking my collaborators. Baptiste Bourget was the main PhD student working on triadic resonant instability. Guillaume Borde was doing a lot of experiment about streaming instabilities that I do not discuss. And Hélène Scola was a postdoc with us working on instability or triadic instability, especially when considering internal wave attractors. Sylvain Joubeau will speak about it later. So Sylvain, Sylvain Joubeau, you know him. He gave a lecture yesterday afternoon, and Philippe Audier will speak, I think, tomorrow. And Antoine Venaille, who is a younger but very smart colleague of us, and Michael Lebas, who was working on this problem with us, who is from Marseille, also a very smart colleague. So I would like to thank you for your attention, and I hope it could be useful. You can send me any emails you want if you want to have a more answer to questions.
Excuse me, sir.
Please, Ramana.
There is a question in the chat box.
So I will try. So I guess your question is related to the appearance of omega plus and omega minus. Actually, you as an experimentalist, you see it from the experimental results. We excite the wave omega naught at the frequency we excite the tank with the generator at the frequency omega naught, which is called to 0.75, and we see omega plus and omega minus. And clearly, you see also that omega plus omega minus is equal to omega naught. So omega plus and omega minus are smaller than omega. And as the frequency, the dispersion relation is omega is equal to n sine of theta. And as sine of theta is an increasing function of theta, it means that omega plus is associated to an angle of propagation which is smaller than the angle of associated to omega 0. And similarly, omega minus, which is smaller than omega plus, is even more horizontal than omega plus. So I think from this picture, you see that the angle of propagation associated to omega 0 is larger than the one associated to omega plus, which is larger than the one associated to omega minus. I hope it is clear for you.
Yes, sir. But can you explain me the origin why it has to split into omega plus and omega minus? I mean, which are the terms actually responsible for generation of that splitting or addition?
So this is what you have. So this is the term. This is this slide which was trying to answer to your question, in which you have the quadratic term here with the Jacobian, and the term here also with the Jacobian, and at the end you have an evolution which is quadratic. So clearly this is the V grad V of the Navier-Stokes equation, which is the origin of the appearance of the quadratic equation. And from this, you get analytically that you have to, this is the reason, the underlying reason for the appearance of omega plus omega minus is equal to omega 0.
I see. Thank you. Thank you so much, sir.
Can I ask something? Hello?
Yes, go ahead.
So I'm just curious if one
can you speak louder?
Hello, am I audible?
Yes.
So I'm just curious whether one can make some connections of the internal wave theory to the shallow water theory, where you allow for additional direction y in addition to x and z, and you assume, I think, the constant density in the layer of the fluid, and you assume that the aspect ratio of that is small in the sense that you can make a shallow water approximation. And I'm just wondering if you can get in some sense make some connection of this theory to the shallow water theory in general.
I'm not sure to be able to answer clearly to this question, so I prefer to skip it.
Sure.
Sorry.
Sure.
I prefer to be honest.
Sure.
Okay, if there is no other question, I thank you.
Sir.
Yes.
So, is the static instability like dependent on the forcing we gave, or it's just coming from the nonlinear terms?
The question is whether the instability is due to the nonlinear terms or to the forcing. This is your question?
Yeah. So, how much does it depend on the forcing? The frequency is present in the forcing.
So there is. This is not easy to understand. To reply to your question. Yes, the frequency, the frequency omega naught is an important parameter for the appearance of different values of omega plus of omega minus. It's not easy to understand to explain the main difference, but the instability, especially this one, but also I skipped the part about superharmonics, in which, for example, Mani and Dheeraj Varma were deeply involved. The instability is very dependent of the frequency, the initial frequency omega naught. It's not easy to answer without a blackboard. I'm sorry about this.
Okay, thanks.
Okay, so thank you. I hope you got some interesting aspect about these internal waves. So I will come back Friday in 2 days in the first lecture, morning for us and afternoon for you, or some of you. And I will say about hydrodynamic solitons directly on the blackboard. Thank you very much.
Thank you, Thierry.
Thank you, Mani. Thank you, Anubhav.